PreAP PreCalculus, Notes 3.5, Properties of Graphs of Polynomial Functions. I think that you'll find in this section is really nothing that's new. We are just combining stuff that we've learned in previous sections to try to give us a better understanding of it. Please ignore the horrible yellow highlighter that you see here. That's just to cover up some text that I'm going to be revealing at some point. Determine the type of polynomial function f, g, and h are graphed below. What type of polynomial function they are, and they're graphed. Give a reason for your conclusion based upon the zeros of the functions. Okay, so if it's based upon the zeros, so we have to determine type of graph, give a reason based upon the zeros. Well, this zero right here is odd because it crosses the x-axis. And also, since it doesn't change concavity, it's not just odd, it's odd and its multiplicity is 1. This one here is definitely an even multiplicity because it's tangent to the x-axis. Now, although it's even, we don't know if it's 2 or 4 or 6 or 8. So we're going to say it's even and it's at least 2. So let's write down some of these things that we just said. F of x crosses the x-axis at x equals 0 and doesn't change concavity. What conclusion can you make from that? X equals 0 has an odd multiplicity of 1. F of x is tangent to the x-axis at x equals 3. What conclusion can we draw from that? X equals 3 has an even multiplicity of 2 or more, or you could say at least 2. Now, putting all that together, if you take the odd number of 1 and add to that an even number that's at least 2, that means the degree of this polynomial is at least 3, and we know that it has to be odd. Therefore, f of x is odd degree and it's at least cubic, which means it's at least third degree. Let's check out g of x. Similarly, we can say that this here is odd, doesn't change concavity, so it's degree 1. This is odd, doesn't change concavity, so it's at least 1. This one here is even because it's tangent, so it's going to be a degree of at least a multiplicity of at least 2. Writing this down formally, g of x crosses the x-axis at x equals -3 and x equals 3 and doesn't change concavity. Conclusion, therefore x equals -3 and x equals 3 have odd multiplicities of 1. Right now our degree is 2 because 1 plus 1 is 2. G of x is tangent to the x-axis at x equals 0. Therefore x equals 0 has an even multiplicity of at least 2. So 1 plus 1 is 2 plus at least 2 tells us that our multiplicity has to be even, and it's going to be 4 or more. Therefore, g of x is of even degree and is at least quartic. Quartic is 4th degree. Looking at h, this is odd, degree 1. This is odd, degree 1. This, once again, we know they're odd because it's crossing the x-axis. Here at 0, it's crossing the x-axis and the concavity is changing. So this is odd, and the degree is at least 3. Writing this down formally, h of x crosses the x-axis at x equals -4 and x equals 4 and doesn't change concavity. Therefore, x equals -4 and x equals +4 have odd multiplicities of 1. H of x crosses the x-axis at x equals 0 and changes concavity. Therefore, x equals 0 has an odd multiplicity of 3 or more. So if we add 1 and 1, we're going to get 2. Plus 3 or more, we're going to get at least 5. Therefore, h of x is odd degree of at least quintic, which means the degree is at least 5. So this is tying stuff together from what we learned in previous sections. And now we're going to look at some terms that are new to us and tell you what those mean, and then we'll get into some more problems. So we begin to study the graphs of polynomial functions. There are other properties of graphs that can now be identified. For the remainder of the lesson, we will define terms, and then we'll identify these terms from the graphs of the given functions. Relative maximum. The point where the graph changes from increasing to decreasing. Label and identify the relative maximums on the graph of the functions pictured to the right. Increasing means as you go left to right, it's going up. Decreasing means as you go left to right, it's going down. So on this graph right here, this point would be a relative maximum. There's another name for relative maximum, and that is local. Local and relative are synonyms in this context. On the graph to the right, relative maximum is increasing from here to here. It's decreasing from here to here. Therefore, this point right here is a relative or local max. Similarly, at x equals 2, the graph is increasing and then decreasing. This is another local max. Local and relative mean the same thing. I should mention that all of these relative mins and maxes and absolute mins and maxes, these are all under the umbrella of extreme values. Extreme values means maxes and mins, whether they be relative or absolute. Relative min is the point where the graph changes from decreasing to increasing. So here the graph is going down from left to right, still going down from left to right, and then once it gets here, it starts going up. Therefore, this point right here is a relative minimum. The next picture, these are both relative minimums because on the left it's decreasing and on the right it's increasing. Should also be mentioned, no, that's good enough. Absolute minimum is the point on the graph that has the lowest y value. Well, this graph here has no lowest y value. It goes down forever. This has no absolute minimum. On the next graph, our absolute minimum is here at 2, -3. It's the lowest point on the graph. Absolute maximum is the highest point on the graph. Here's an absolute maximum. For this graph, that's at -2, 6. And this next one doesn't have any. No absolute maximum. A couple more terms. Point of inflection and intervals of concavity, which we've talked about intervals. No, we haven't talked about intervals of concavity. Point of inflection, also known as an inflection point. A point where the graph changes concavity. So like, for example, if I have a curve that looks like this, and the rest of the curve looks like this, that red part of the curve is concave up, the blue part is concave down. That black dot is called the point of inflection. It's where it changes concavity. Intervals of concavity, open intervals along the x-axis where the graph is concave up or concave down. We'll get into some examples of those. Point of inflection can occur at one of 3 places. It's going to occur at a 0 with an odd multiplicity of at least 3. We've seen that happen already. Between a 0 of odd multiplicity of at least 3 and the nearest local min or max. And then this next part is important. I've underlined the word approximately. Point of inflection is approximately halfway between those points. So as an example, so in this graph right here, first part said at a 0 of multiplicity of at least 3. So we know this one is here because the concavity is changing, so that's at least 3. And then the second one said between a 0 of multiplicity of at least 3 that's odd, which we just pointed that out, and the nearest local max or min. So it's between this point and this point, someplace in here there's an inflection point. It's about halfway between them. Here is a maximum. Here's an inflection point on the x-axis. So in between here, there's going to be another inflection point about halfway between. 3, between consecutive extreme values, it's about halfway between those. So like looking at this problem here, looking at G, here's an extreme value or here's an extreme value, about halfway between is an inflection point. That's what that's suggesting. We're going to stop the notes there, and then we'll do some examples on the next video. And basically all we've done here is we've reviewed multiplicities of zeros, and we've given you some new terms, minimums and maximums, relatives and absolutes, styles, and points of inflection.